Yeah, hi. Good evening, everyone. So just give me 1 2 minute so that I can join with my left iPad. So this is week 4 of our class. Okay. Okay. So this week, I think you have learned about that Viterbi decoding for our hidden Markov model, then parameter learning. Then we also learned a lot of new algorithms this week. Yeah, like the algorithm that expected maximization algorithm and all. So like every week, so we solve our question. So to this week also I have some questions with me. So we'll be trying to solve them, and along with that, we'll try to learn the concept. Okay, fine. So this algorithm is an example of forward-backward algorithm on or a special case of the expectation maximization algorithm, or both of it. So this was in the so you can write your answer in the chat box. So that will be very helpful for me, like so that you can participate like that. Yeah. So this was in the lecture 2 of our course. So I think you have already seen the videos from Professor, uh, where using this algorithm we try to learn the parameter of the hidden Markov model. Yes. So yeah. So one is saying that this is a forward backward algorithm. Uh, yeah, most of you have answered that this is a forward backward algorithm. Uh, okay. The first thing is that why do we need this algorithm? That's the important question. So this is the expected maximization algorithm that we know, but why do we need this? So the main thing, so all you have given the answer A, but the main thing is that why this is important. That we know that this is a expected maximization algorithm. Yeah. So this algorithm is used to find the maximum likelihood estimate of the parameters of our hidden Markov model. So last week we have already seen the hidden Markov model, the Viterbi decoding and all. Like we have seen the Viterbi decoding. Then we have seen that there are multiple possible ways for the Viterbi decoding. So that Viterbi decoding was the dynamic programming approach. So first we found out the cheapest cost to state j at each step. Then we backtrace them from the state to the best predecessor. But there are three parameters we need for this. Okay. So the thing is that, yeah. So suppose the concept is like that. As you all are about that aware that this is a NLP class, and we are about to learn the statistical machine learning algorithm. In this course, we will be mainly learning the statistical ML algorithms. Okay. So in suppose you are given a text like this that promised to back uh, the bill. Okay. Now, so you are promised to back the bill. Then this promised can have parts of speech as VBD or VBN. Okay, this is two the determinant, and then it can be RB, it can be noun, it can be JJ, and it can be VB. Okay, then it can be determinant, or it can be VBN. So these many possible paths are there. Okay, so basically what I want to say that you can go from here, then here, then you can go here, then you can go here, or you can start from here, then go here, then from here you can go here, then here, then here. So anyone is a possible path. So here you can see that you have this possible path, this possible path. So which one is the best one? Okay. So to know this, we developed the Viterbi decoding for this our hidden Markov model. So using the dynamic programming. So this we called that delta J is okay. So this delta J is the this is the cheapest path until this state. Okay. Now so what will be this? This will be delta J plus one. Sorry, delta J S plus one. Okay, this is the state. Okay. Now for traveling from this state to this state, you need this P Tj given here. Okay. So this is the way. So you have possible, I have shown you the possible ways. Okay. So then how I calculate my delta ij? So I calculate my delta j using s plus 1 is equal to, this is the maximum of all path 1 less than is equal to I, 1 less than is equal to n, 1 I less than is equal to 1, I greater than is equal to 1, less than is equal to n, the previous path. Okay. And this transition probability, which is PTJ given TI into probability of, so this is the emission probability, and this is the transition probability, that is WS plus 1 given TJ. Okay, so so this is the transition probability, this is the emission probability, and this is delta I, this is the cheapest part with this state. Okay, and how I find out my psi j? So which is basically nothing but is equal to the argmax. So a maximum is like you are finding the maximum element, and argmax will give you the index. Index, suppose you have an array like 0, where this is 12, this is 99, this is 80. So argmax will give you the index that your maximum element is at second position. Okay. So now we have some parameters for our hidden Markov model. So this is what I was describing, that the Viterbi decoding algorithm. So you have some parameter respected to this hidden Markov model, which is pi. That is the probability that a state start with a sequence. Probability that a state start with a sequence. Okay. Now, second thing is that your probability of transition from one tag to another. So what is your tag? This is your tag. So this is a T, this is a T. These are T. Okay. So now so these are the parameters. So what are the parameters? Parameters are pi. Then you have probability of transition from one tag to another, okay, which is probability of tj given tr. So that means that you are at this tag. So what is your probability of transition from this verb to noun? Okay, so this is the probability, and this is the parameter for it, and emission probability, emission probability. Okay, so that is probability of word given the tag. So like I don't know that whether this the will come after the back or not. Okay, so why we need this parameter? Basically, you have this. So this is a sentence. Okay, this sentence is given to you. So you are training your model with this sentence. Now you have to find. So you are training this model, and somewhere later you will do the inference. Like you will give some input to your model, and you are expected to get an output from your model. Okay, so that's why you need to tune these parameters. So you need to find out these probabilities and save somewhere. That's how you can. So that's how you can. So sorry. Yeah. So that's how you can find out the parameters. Okay. So this is the thing. Yeah. Now, so these are the parameters. Now, what we have to do that we have two scenarios here. Like you can be given a label data set. Um, a label like you are given a dictionary or sentences and all. Your this label data set is available to you with POS categories like this. Like so this is the sample sentence. Like I have just giving example with a simple sentence. So maybe you are given hundred or thousands of sentence like this with the POS tag. Okay, so your POS tag is already given. Now fine. Now so that you can run your model and step and you can find these probabilities. This probability you will find for all of the all of these all for all of these data set, and you will save this and you will use that parameter for your inference. Now, the second scenario is that your only corpus is available, like that only the sentences are available. You are not given this POS. Then you have to find out something, find out a way. Okay, so so what will you do in that case? So if you are given the POS and if you are given the sentence, then your parameter can be estimated using the maximum likelihood estimator. But if these are not given to you, then what will you do? Okay, so that's why this worm Welch algorithm came into the picture to estimate the parameter of the hidden Markov model. Fine. So I think this is clear to you. Now, so this is the expected maximization algorithm given the sequence. So you are given this sequence only, you are given this sentence only. Okay. So you have to estimate the parameter. So this theta is equal to parameter. Then you have to estimate a b pi. Okay. So are you getting the point? So this is nothing bad. If anyone have any difficulty in understanding, they can type that in chat box. That what are the hmm, hmm, what are the problems? So they can ask their question in the chat box. I'll definitely give reply. Okay. So so in a easy term, suppose you are doing a linear regression kind of thing. Okay. So suppose this is your data points. Okay. Now you have to fit a curve along it so that you can. So this is why all that this is why this is a and this is a line. So this is the best fit line. So for this, whenever I will give a x, this will give me a y. I will give this x, this will give me a y. So basically this is a data point. Okay, this data point, what it says, this is your given data, this is your trained data. Now how will you test it? So you will fit this line to your model, to your data point. Then you will give a x and you will get a y. Okay. Now, mm, so what are the parameters here? So you know the equation of the line is like p max plus c. So this c set. So here two cases can arise. Like this can go up or go down. So the line can go up like this. Line can go down like this, or what can happen that it can be tilted like this. It can be tilted like this. Okay. So these two things can happen. Okay. So this C is the intercept. So this says that the where this line meet the y-axis, and this M says the angle. So that's how, using this data, you fit the line and you get the angle and the C. Okay. So this is the two. These are two parameters for your linear regression model. Same like that. This model, this HMM is, or this beta B decoding for the heroic Markov model has these three parameters, which is A, B, and pi. So I have described these to you. What is pi, what is A, and what is P. I think this is understandable for you. Okay. Yeah. Now how will you solve this? So you will determine the probable paths. Okay. Then you count the expected number of transition aij, as well as expected number of times various emission are made. Then you would estimate this until convergence. Okay. So so our question was that it is a forward backward algorithm, and it is a special case of expected maximization algorithm. Of course, this is a forward procedure algorithm, because like suppose you are given like alpha it is equal to probability of y1 is equal to y1, or like yt is equal to yt, and xt is equal to I given theta. Okay. So this will be the probability of seeing this sentence y1 to yt and being in state I. Okay. At time t. So we found it recursively using alpha it is equal to pi I bi y1. Fine. Okay. So now I think this is clear to us that this is a forward backward algorithm, and this is a expected maximization algorithm. Okay. So both A and B is correct answer. Okay. So both A and B is the correct answer. So I have tried to give you some sense of this Baum-Ulch algorithm. Then we can, yeah, we will find another question also like later, so that we can that time we'll see that how this algorithm we can solve it, some problem using this algorithm. Okay. So can you please try this question and tell me what should be the answer? So here in this question, so once a day, as first example, at noon, at 12 p.m., the weather is observed as one of the state one, rainy state, uh, or cloudy state, or sunny. The state transition probabilities are given like this. Okay. Now you have to find it out given the weather on the day t is equal to 1 is sunny. Uh, Given that weather on day one, at day one weather is sunny, what is the probability that the weather of next 7 days will be sun, rain, sun, cloudy, sun? So you have to find out these probabilities. So you all use your phone to check the weathers and all. Uh, so this is how, like, before the ML, before uh, uh, pure ML model or deep learning based model came into picture. This is the way how statistician try to forecast the weather. Okay, so this is a statistical way of forecasting the weather. Yeah. So can you please try anyone and tell me that what should be the answer? So what algorithm will you use basically? So that's the main intuition for this question. So you know that you have already learned about the Markov chain model, where your state transition probability is given. Okay. So what are the state here? You have to find out that what are the state here and what are the transition probabilities here. Okay. So what is your state here? So I think you are trying to at least solve the question from yourself. Okay. So what are the state? State is state one is rainy, state two is cloudy, and state three is sunny. Okay. And this is the probability given to you, the transition probability. So what is this? This is a transition probability. Okay. So this state is given to you, transition probability is given to you. So you have to find out the answer. So what you have to do here? So you have to compute the probability of the given sequence. So you know what is the sequence. So sequence is given here. Okay. So your sequence is that is I don't have any charge in it. So the sequence is given to you. That is this sun, rain, sun, cloudy, sun. Okay. So from where you have to find out the that probability of transition, that from which state it is going to which state. Okay. So and you have to just multiply the probability and write the answer in the chat box. That's it. Okay. So for this, we can draw the picture. So we can draw the our state like this. This one. Like this is sunny, this is rainy, and this is cloudy. Okay. So what you have to do? Yeah, Lalita given the answer that is 0.0092. Okay, let's take it out here. So what I have done that yes. So our state is this. This was the S3, 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 S1, S1, S3, S2, S3. So this is, but I just replaced with this one. Like this is S1 means sunny, rainy, S2 means cloudy, S3 means sunny. So I had this sequence. So I had the sequence sunny, sunny, sunny. So this is the sequence. So I have just written like this. This is sunny means S3, then S3, rainy means S1. So S3, S3, S1 like this. S3, S3, S1. So this is how I have changed that. Change that. I have written the states. Now, given, so I have to find out the what is the question here? So I have to find out the probability that the weather for next 7 days. Okay. So I have to find out that this should be my state given my model. Okay. So why here this is written as my model, because you are given the transition probabilities. That means somehow you had the data, you have some data, and from this data you already saved these transition probabilities using the Guitar algorithm model. Using some algorithm, you have already saved your model, and you are using your data to do this inference. Okay. So then what happens? That this means the probability of S3 into probability of given S3, probability of S3 given S3. So like this. Okay. So that means like so so this basically means that the first days you don't know what should be the first day. First day should be sunny or rainy or cloudy. You really don't know. Now for the second days, yeah, you know that you have to calculate that what should be the probability of sunny given that the previous day was also sunny. Got it? That's why here is a S3. Now for this one, so I am here. So I have to find out the probability of sunny given the previous day was also sunny. Fine. Now for here, so I am here. So I have to find out the probability S1. That means maybe it was cloudy, uh, so that the previous day was sunny. So this is how I have to calculate. Then that means that here for the first one, I have to find out the Q3. Then I have to find Q3 means that find out the probability of the state is sunny, and for the rest of them, for the rest of this, so this is the transition probability. Okay. So what is the probability so that first day is sunny? First day is sunny. Okay. So from here, I get this information that given that the weather on day one is sunny, that means I know that weather is sunny. So that's why I am very sure. So that's why it is given it is 1. Then what is the probability that S3 to S1? Let me write it down here. So S1, S2, S3. Okay. So S1 was rainy, S3, S2 was cloudy, and this is sunny. So this means that S1, I can rewrite this as S1, I can rewrite this as S3, S3, and I can rewrite this as S2. Got it? So what is the probability of uh, S3 given S3? That means S3 given S3, this one, 0.8. So that's why this is 0.8. Got it? Now I want to calculate this one. Probability of you know that this S3 given S3 is again 0.8. Now I want to calculate this one. Probability of S1 given S3. So that's why S1 given S3. So that's why I want to find out Yeah, from here. So this I can see this is 0.1. So that's why 0.1 is here. Got it? Now I have to find out S1 given S1. So S1 given S1 is this one. So that's why 0.4. Okay. S3 given S1. S3 given S1. Okay. So that's why I have to find out this one, which is 0.2. So this is how you have to calculate it. And the answer will be 1.536 into 10 to the power minus 4. I think Lalita, you made this little mistake only. So if if you don't think that I am doing the correcting, you can write in the chat box also. Like maybe you have done some small mistake. Okay, okay, great. Okay. So our answer, our correct answer was this one. A. Okay, fine. Now we can move to the second next question. Okay. So in question two, the expected number of consecutive days of sunny weather is. So here it's not like that you will calculate the sun, rain, how many days it was, and you will tell that how many days there were sunny. So this is not like this. Okay. So I have to find out sun. So this was this. Okay. Now my question is that the expected number of consecutive days of sunny weather. Okay. So this is the question. Now how will you answer? I can write the question here. Question is expected number of consecutive days of sunny weather. Okay. I have to find out this. So what we need that we are interested in the expected number of consecutive sunny days before transiting to another state. Okay. So we have to use the expected time in a state formula. So what is the in Markov for Markov process? The expected number of consecutive days in state S before transiting into the other state has a formula which is given by S is equal to like this. Okay. It means probability of there are two sunny days. Uh, you can see that sunny is 0.8. So you just have to plug in this formula only. So yeah, so this is the formula is the expected time in a state formula. Okay. So what is the expected time? So you will be in a particular state. So here our state is S. Okay. So this PSS that is the probability of remaining in the same state. Okay. So I know this is 1 minus 1 by 0.8 from here. That this is sunny and this is sunny. Sunny, sunny. So here the answer is you can calculate it on like what will be it? I think it will be 0.2, and then 5. Yeah. So this is the solution. Okay, fine. Now this is the next question that you are building a model distribution for an infinite stream of word tokens. Now you know that the source of the stream has a vocabulary of size 1200. Okay, so this is important to you. Now, out of these 1200, you know 200 words to be stop words, each of which has a probability of 0.001. So stop words means full stops or comma or like i- or exclamatory sentence or question mark like that. There are 200 such words like this, and each of which has a probability of 0.001. Okay. Now, with the with only this knowledge, what is the maximum possible entropy of model distribution? Okay. So read the question carefully and try to solve this one. So this is a question from entropy. So if you know the entropy formula, this is a question from entropy. So you have to understand that how entropy is calculated. So what is the entropy? Maximum possible entropy. I think here this is given that base for entropy calculation of base 10 here. So what is PXI? Can anyone write in the chat box what is PXI? No, Bhaishali, this is not a correct answer. 001, 0.001. Yeah, and this is also not in option. So I'm just asking that what is PXI? So PXI is the probability of the ith word in the vocabulary. Okay, and we sum over all 1200 over 1200 words. So what you have to do, what information we have given. That's the main important question now. Okay. So we have vocab size 1200. Okay. Then we have 200 stop words with probability 0.001. Fine. Now we have remaining, how many words are remaining? Remaining we have 1000 words. Okay. So so we have total 1200. Among them 200 are stop word and others are 1000 words. So they must sum to a probability of 1. Okay. So like all 1200 word must sum to probability 1. So that's why I know that for these 200 probability is 0.001. So what I can do that 1 minus 200 into 0.001, which is 1 minus 0.2, which is 0.8. Okay. So what is the probability of this 1000 words? This is 0.8. So the probability of each of these 1000 word, we assume that this is a uniform distribution. Okay, so that's why if this is a uniform distribution, then only if our probability distribution is a uniform distribution, then the entropy is maximized. Okay, so that's why this probability of this non-stop word is basically 0.8 by our 1000, that is 0.008. Got it? Now we have to compute the entropy. So for entropy, we know the formula. What is the formula? H is equal to minus of sigma I pi log pi base 10. Okay. For so we have two possible scenarios. We have 200 stop word. Okay. For this I can write this as H stop. So I want to find out the entropy of the 200 possible stop work, which is minus 200 into 0.001 into log base 10 0.001. So I think you can calculate this by your own. What will be this? So this is minus 200 is same, 0.001 is same, and this means 10 to the power minus 3. This 0.001 means 10 to the power minus 3. Okay, so that's why you will be multiplying it to minus 3. Okay, so how much will you get? Mm. So I think you will get, so this is nothing but this minus minus will plus 200 into 0.003, which is 0.6. Any problem? So we have found out the entropy for stopwatch. Now we want to find out the entropy for the remaining words. Okay, remaining non-stop words. Okay, what is the remaining non-stop word? I have to find out the remaining non-stop word, which is H non-stop equal to minus 1000 into 0.0008 into log base 10 0.0008, because I have found out this one. I have already shown you that how I have found out this one. So here I am putting this value to here. Okay. Now what will be the value here? 1000 into, can anyone tell me how can I do this? So what will be the what will I do for log 0.0008 is equal to log base 10? I know. Okay, it is given 8 into 10 to the power minus 4. That means log 8 base 10 plus log 10 to the power minus 4 base 10. That means, so you can calculate this. Okay, log 8 base 10. This is not a big deal. So if you calculate this, how much will you do? Hmm. So you can calculate in your phone only. So it is 0.9. 0.9 plus it is minus 4. That is minus 3.1. So am I right? Can anyone confirm once? So you understood this whole this thing, how I am calculating all of this. So I have to find out the entropy of stop words and non-stop word. So these are the simple calculations for. Okay. So now H non-stop, okay, which will be minus 1000 into 0.008 into minus 3.1, which I have found it out. That's equal to 1000 to 2.48. This minus cancel out. That means 2.48. Fine. Now what is your entropy? Entropy is H stop plus H non-stop, which is 0.6 plus 2.48, which is 3.08. Okay. Any problem? So is this clear to you? So I think this will be the answer. 3.07. You can find the solution here. Okay. I think this is clear for you. Then come to our next question. Okay. Please try to solve this one. So okay, fine. Now, so the question is given like you are given this word that is input sequence, which is Sachin Tendulkar is a great player. Okay, now you know that possible tag for each word is for Sachin. We can find out these four tag. For Tendulkar, we can find out these four tag also. Is a verb, is determinant, a great adjective. Then for player also, there are three possible ways. So here we have four possible ways. Here we have four possible ways. One, 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 three. Then from this, so you have this all of these choice. Okay. Now what you have to do? So you have to find out that how many possible hidden state sequence are possible in the above sentence and state. So for this Sachin, you have four choices. Tendulkar. So basically, first what we have to do, we have to identify the number of possible tags for each word, which is already given to us. Now we have to compute the total probability, total possible hidden state sequence. So what is the total possible hidden state sequence? Okay, so which is 4, 4 into 3. So basically 4 into 4 into 1 into 1 into 1 into 3. So which is nothing but 48. Okay, so now tell me, what is the possible answer? So this is not 48, this is not 48, this is not 48. So this is 3 into 16. So this is the possible answer. Okay, so this is the correct answer. Now come to this yeah, like what are the space and time complexity order of the Viterbi algorithm? So in the beginning of our lecture, I have already told you what is the Viterbi algorithm, and if k is the number of state and n is the number of time stamp. Okay. Okay. So how do we calculate it? So what is given to us? So let's solve this. Okay. So so what is the how we initial like how we analyze this time complexity? So we have given that k is the number of state in our hidden Markov model. Okay, and n is the number of timestamp. Okay, or you can say that n is the length of observation sequence. Okay, so this is given. So how we analyze the time complexity? So what we do actually in our Viterbi algorithm? So in Viterbi algorithm, let- so in Viterbi algorithm, we do first we do the initialization. Fine. So this is time step t is equal to 1. Okay. So we initialize probabilities for all k state. Okay. So on the initial state distribution. So to initialize all init for all k state. For this you need order of k time. Okay. Now we solve it recursively. Okay. To solve this recursion for each timestamp from t is equal to 2 to n is the sequence length. I have already mentioned here, n is the sequence length. Okay, to solve this recursion for each state at time t, we compute probability of transitioning from one state to k state. Okay, we we can write this like we can compute the probability of transitioning from each of the k state. Okay, at t minus 1. Fine. This involves you have to consider all all previous case step, and then you have to compute transition probability for k possible current state. Okay, so this will be the total number of computation here will be k square. Fine. Now you repeat it for n time. So that's why it will be n into k square. Got it? Now, so this is how you find out that this is your time complexity, k square into n. Okay. Now we have found out that yes, k square into n is our time complexity. Okay. Now we have to find out the space complexity also. So for space complexity, what you do that to efficiently compute the base sequence, you have to maintain two things. That is, so this is the space complexity. How we found out the space? That is, you have a 2D table. You have a 2D table or 2D matrix with what should be the number of rows? Number of rows is the k state. Okay, and number of columns there are n columns. Okay, so that's why you need a table of size kn. Okay, so that's why kn is your space complexity. So this each entry stores the. So what are you storing here? So you have to store the maximum probability of reaching a particular state at a given time. So that's why you have to maintain this. Okay. So for the back pointer also, you store if you store this, you can back point from here to here. Okay. So you know that in what happens in dynamic programming. So this is same the dynamic programming. So I think A is the possible and solution also. Okay. Okay. Now this is our last one. So this says that Mr. X is happy someday and Mr. X is not happy always. So he is happy someday and angry on other days. We can only observe when he smiles, frowns, laughs, or yells, but not his actual emotion state. Okay. Let us start on day one is a happy state. So this is given to you. This is important information to you. Now, there can be only one state transition per day. Okay. So this is like sunny. There can be only one sunny day, only one rainy day, only one cloudy day. So that's all. Right? Now, it can be either a happy state or an angry state. So the HMM is shown below. Assume the QT is the state value of day t and OT is the observation on day t. Answer the following question. What is the probability of O2 that he is running? Okay. So you can see the probabilities from here also. You can, if I zoom it, you can see. So what we need to do? So you have to find out the probability of observation. Okay. So probability of observation, that is on day two it is wrong. Okay. But we don't know whether he is happy or not on day two. Okay. We know that he is happy on day one, but we really don't know that he is happy on day two or not. Okay. So hence the probability of the observation is the sum of product of the observation probabilities and all the possible hidden state transition. Okay, so now, so what does it mean? That is, this is basically probability of O2 is equal to front. So you can front if he is happy on that day, or probability of O2 is equal to front if he is angry on that day. Okay, so we have to find out this one. So so what is possible? So probability of, so this state is happy. So you know this state. Okay. So this means that probability of Ron given he is happy into probability of happy, and first day also he was happy. Probability of Ron given angry into probability of angry given happy. So this is the answer to your question. Okay. So which comes out that from here you can find out this from given happy, that is 0 0.1 into from to happy, given that next day also he is happy. So this is 0 0.8. So this is 0 0.8 plus probability of from given angry. This is 0 0.5 sorry, multiplied by probability of angry given happy. So this one angry given happy, which is 0. So which will be 0.2. Okay, so which is 0.08 plus 0.1 is equal to 0.18. So 0.18 is the answer. Right? So this was the last question available to me, but there are 40 minutes left for our class. So you can utilize the time. So how can we utilize the time? So like previously, I also told you that I'll try to uh, I will try to share you like how like the large language models are basically being used nowadays. So to reach to the large language model, we need to know something like how. So there is a option of raise hand, I think. So can you write in the chat box also that how many of you know about RNN, recurrent neural network, LSTM, GRU and all. So basically, the next part of our lecture, will try to cover the how from the transition of the statistical model to the neural network model. Okay, so that's why I stopped my screen and I'll be sharing the other PPT. So uh, which from a class called Recent Advancement in Large Language Models from Professor Tanmay Chakraborty of IIT Delhi. So I'll be sharing the document. Give me a second. So meanwhile, you can tell me that. Do you know RNL, LSTM and all? So how many of you know RNN, LSTM, these models? Okay, fine. Mm, okay. So let me share my screen again. Mm, Okay, so as I'm, this all credit goes to our Professor Tanmay Chakraborty. So I am just adding his slide because I didn't make this slide. Okay, so so from where we will start that. So this is a thing that how your word is being represented. Okay, so suppose you are writing a word like hotel, conference, or motel. So uh, so for that, like you have a big corpus, then how will you represent this word? Okay, so then suppose you are doing a one hot representation. That means like in this one hot representation, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 word. So we know that with 15 word, we can make a dictionary because dictionary is a very large thing. So we can so if I have a dictionary of 15 word, I can use this one or encoding like this. Okay, this represent here if we have one and other zero, we can represent motel or here I can represent hotel. Okay, but in our vector dimension, the number of word in vocabulary is around 5 lakh plus. Okay, so that's how if you generate an array of 5 lakh, so you really cannot process it. Okay, so your one hot representation will be 5 lakh cross 5 lakh. So you don't have such memory to load this matrix. Okay, so you have RAM. How what is the maximum RAM you have? So you have maximum 1 GB, maximum 32 GB or 64 GB RAM in your system. So you really can't load a 5 lakh cross 5 lakh matrix in that RAM. So so the problem is this discrete symbols is that this is orthogonal. That means if you do the multiplication of this term, that will become zero, and no natural notion of similarity. So you can't find a similarity from this representation. So could can we try to rely on wordnet's list of synonyms to get similarity? So this is how they are. So they have some they had a WordNet tree. So that is a database basically database of words, but they have uh, uh, 1 lakh around 1 lakh noun, 11,000 verb, 22,000 adjective, and 4,000 adverb. Okay, so if you use this WordNet, if you use this database, then using the syn set or synonym set, the set of near synonyms, uh, instantiates a sense or concept with a gloss. That means, suppose you have a word chump. Okay, so you know that a word has many meanings. Okay, so one word can have many meanings. So that's how this champ can have 9 meanings. That is champ, fool, girl, mark, Petsy, fall guy, sucker, soft touch, mug. Okay, so this champ has 9 cents. Okay, so this wordness is the database. So this can't really uh, consider these 9 senses also. They never because for each word there is not 9 sense. Okay, some word there are more senses rather than some word. Okay, so you can't find a really a good database to to save these uh, 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 senses. Okay, so that's why what is people doing? So people is doing some count-based method so that people is finding the co-occurrences of forward similarity that this artwork or digital comes together how many times. It has been seen that digital and computer is kind of related word, so that's why it came together 2 times. Then information and data came is a similar word, that's why it came together 6 times. But pinch of salt, we know that pinch of information we never tell, so that's why it never appear. Okay, so we can find out the co-occurrence of word similarity, and from the from there is a brown corpus also. Okay, but if two words are similar in the meaning, if their context vector are also similar. Okay, but there is a problem in this raw count. Okay, so we have already in last class we have seen the TF IDF instead of raw term count. Okay, so basically we can count this raw. Okay, but the problem is that you will found that there are many full stop in your sentence in your database. So you will count this 100 times. Okay, 1,000 times. So basically, uh, suppose what I say that Netaji. So Netaji came only twice in your database, but this full stop came 1,000 times. So this full stop will get more priority than Netaji. Okay, or Gandhiji. Okay, so that's why we can't use this raw count. So that's why we are using kind of what is called TF-IDF, what is called term frequency and document frequency. TF means term frequency, IDF means inverse document frequency. So where DF is the number of documents T occurs in. So there are now in my database now I have multiple documents. So uh, I can find out that Romeo came into 113 time in document 1 and action came into 130 time in 31 document. Okay, that means you can see that Romeo can found in only one document, whether action can be found in 31 document. That means Romeo is an important word. But how should I make my computer or make my algorithm understand that this is an important word? So that's why I can find out the IDF, that is inverse document frequency, which is n is the total number of document, and DF is the you're finding out the DF. So you're finding out the DF here, how many time it is calculated. So this is how TF-IDF is calculated, but there is a drawback also. That is, you are always saving a matrix of quadtex complexity. Okay, so that's why space complexity will increase and relative position and order of words are not considered. So that's why you need something more. So that they are this. So the problem is that the big matrix. So so you can fix this problem by dimensionality reduction. So you can do PCA kind of approach. So in PCA, you know that we use SVD. Uh, so in PCA, we basically do the eigenvalue decomposition, as there is that is a square matrix, but it might not be a square matrix. So that's why we do the singular value decomposition. Okay, so you can do the singular value decomposition and save the important matrices. Okay, so that can help. Now I have some prediction based method. So till now, what I was trying using the TF-IDF, I was trying to give you the intuition that how the document frequency and inverse document frequency is calculated. That is that how you can represent a word. So first it came into our mind that we can represent a word using the one hot vector. Then using the TF-IDF, we can see its we can see its frequency and all. Now we came into the thing that is called word embedding. Okay, so word embedding is a dense vector. So it is the newer version of our one hot encoding. So it is dense means like so in one hot you can find many zeros. So that's why it was a sparse matrix. Then so now here we have a dense vector. Now it helps in learning parameters. Many may generalize better and capture synonyms better. Okay, so here they are calculating the word to vec. So this has two. So this word to vec is a neural network model. We have two algorithms. One is continuous bag of words or CBAW. One is skip graph. Okay, so there are two algorithms here. So in SIBA, we use a window of word to predict the middle word, and in skipgram, which is the opposite of this, is a use a word to predict the surrounding word in window. Okay, So basically, what is it doing? That suppose you have given a word like you have given a sentence like this. Okay. So basically, in we have two algorithm, which is cbow and skipgram. Okay. So in cbow, you are looking into your target, and you know this is your surrounding words. Okay. This is called positive words, and these are the negative words. Okay. So you are taking a plus minus two word window, giving training sequence. So what you are doing that you know that in skipgram classifier, train a classifier that given a candidate word and context pair, it can assign each pair a probability. So this is my goal. Okay, my goal is that I will be given my target. Okay, with the context word with the context, like context means apricot jam or apricot adverb. So apricot is related to jam, but we know that apricot is never related to apricot. So I have to find out the uh, I have to assign each pair a probability. So I don't discard it. I have to assign a probability. I want to assign a high probability to it, and I want to assign a low probability to it. Okay, so that's why so this is my goal. So how I solve this goal, that uh, we know that we can compute a similarity using the dot product. Okay, so which is like w dot c. Now this similarity can be calculated like this. Now we can use we can turn this probability into this equation. So this is the sigmoid function. Okay, and this sigmoid function we know, which is 1 plus e to the power minus x, and this is given like this. Okay, so this is the count, and this is the context, and this is the word. So what I do, I found out the similarity of the context and the word using c and w. So I do the dot product and find out the similarity, and then if I if I if I if I if I pass them on the using the sigmoid function, this will as the logistic regression, this will give me the probability. So I have a sequence. I don't only have a single word. I have a sequence of words. So that's why I am doing the multiplication. Then for this I am taking the log. You know that this log. Uh, if I do this thing, so the main thing is this one. The embedding, we will need a set of W for a set of C. Okay. So this W is the target word and C is the context or noise word. Okay, this is how our embedding will look like. So this is the goal of this introduction. So this is how word will look like. Then using this, so basically these will be the positive samples: apricot and tablespoon, apricot plus off, apricot plus jam, apricot plus A. So these are the positive samples. And what are the negative samples? Apricot plus aardvark, apricot 7. So basically apricot lemon, apricot A, apricot pinch. Okay. So these are the negative samples. So using this positive and negative sample, we can find out the probability. We can find out the probability of choosing a negative sample. Okay, count of w to the power alpha into count of w dash to the power alpha. So alpha is 0.75, gives a better performance because it gives their noise word slightly higher probability. Okay, so this is the loss function, and this is how we learn the classifier to find out the word to take representation. So this is how we do this. So my intuition for this was that you should know that how what to bake calculates this one. So this will come. So I am just maybe I am just running here because this skipgram or Sibau context will come into our lecture later part at week 5 or 6. Okay, so that's why I am not giving it a higher priority now. So the main thing is like this. So what was our main goal? So I told you that I like pizza lots of. I can choose cheese, corn, or tree. Okay, so I have to predict the word here. So I can predict the cheese or I can predict the corn. So what should be the given probability? Okay, so we can recall that our language model, we can assign a probability to a piece of text. Okay, so suppose if we have some text x1 to xt, then the probability of this according to the language model is probability of x1 to xt is probability of x1 into probability of x2 given x1, then probability of xt given all the other words. Okay, that means what does this mean actually? That means probability of given corn given I like pizza with lots of. If I have to find out probability of off, then it will be I like pizza with loads. Okay, so this is like this. So this is our this is what our language model provides. Okay, the probability. So this is the multiplication of probability of xt given xt minus 1 to x1. Okay, now how to build our, so this is a language model, gives us a statistical language model, but how to build a neural network to find out the probability of xt plus 1. The problem setting is same, that you have to find out the xt. So here also you have to find out the xt plus 1 given all the other words. We can do two things. Suppose we are doing a name entity recognition. Name entity recognition is a task in NLP. So maybe you have name it. What does this task means? Suppose you have to, in this you have to find out which word is saying you about the location. Okay. So this is the important task, because like whenever you type something in your chat GPT, it says that it gives you a answer very nicely, but you never say that um, how you identify, suppose how you identify the location and all. Okay, so that's why this came into the picture. This I have to find out that this Paris is a location. Okay, so for that I can feed this. I can I can find out the one hot encoding and feed this to this layer. Then W is a matrix. I can multiply it. I can pass this, and I have a sigma kind of function, kind of activation function, which will give me a probability of location. Okay, but the problem is we have a fixed size window. Okay, so that's why if you have a fixed size window and you are doing something like this, so you are basically finding out the probabilities that this if you want to do a next word prediction, what will be the next word here, then the students opened their laptops or books. Okay, so this will give you a high, the book is giving you a highest probability. So how we are calculating this? So this x1 is a one hot vector. Okay. Now we are concatenated word embeddings with this e1, e2, e3, e4. Okay. So using this one hot vector, we are finding the concatenated word embedding. So this was the e1, e2, e3, e4. Then this is my hidden layer. Okay. So basically, so this is my hidden layer. So in this layer, I am doing f of we plus b1. Okay. Then in this layer, I am doing softmax of uh plus b2. So this is how neural. So w is a matrix. Okay. So e1, e2 is a matrix, and w is a matrix also. So this is e1, e1, e2, e3, e4. So these are the rows, and w is a matrix. So where I am basically calculating I am basically multiplying this matrix and finding out the similarities. How you know that how neural network trains. Okay, so as there is no need to no need a we need a neural architecture that can process any length of input. Okay, so but here our window size is fixed, so this is a problem. Okay, so that's how we have to discard this model. So what I can do, so that's how the RNN came into picture. So in RNN, at each step, you can give a word. So x1 you can give here, x2 you can give here, x3, x4. You can go up to any step. So that's how this model we discarded. This neural network, this is the fixed window neural language model we discarded, and we came into the RNN kind of architecture. Okay, so I think this is enough for today's. Okay, I might show you the next slides and in next class. Okay, so that's all. Thank you for joining. Okay, so if you have any question, you can ask me. Meanwhile, yeah. So maybe on the next upcoming week, we'll see that how RNN and LSTM is working, and then we will move to the transformer. We can see that how transformer is working, and also like this is a like small 20-minute part of this class. Okay, so mainly we will be focusing on our NPTEL's course videos. That is the sir, I missed my assignment, so can it be redone? I don't know. Like I think it can't be redone. Okay, so please try to do it within the timeline. Yeah. So this is a machine-driven thing. So we have some script written into our machine that open through this mail. So like the mail will be thrown to you. You will get the. So today's timing was changed. I had some previous class to take, so that's why I changed the timing. So maybe for next 2 week also the timing will be from 7 p.m. and then rest of the week the rest of the remaining will be the same from the 6 p.m. Okay. So please notice the timing also. Okay. So thank you so much to everyone. So Debajyoti, it is a machine-driven thing. So there is no human intervention. So I really can't help with your assignment. Okay, fine. Thank you so much for joining. So okay, bye. Good evening or maybe good night, everyone. Okay, thanks for joining. Yeah, thanks Lalita and Tiva. Okay, thank you.